sounds to which we normally listen, for instance over the telephone or over radio, must have been amplified hundreds of times before we can hear them. For example, the output of a microphone must be amplified before it can produce an audible sound through a loudspeaker. A device used to accomplish this is a vacuum tube amplifier, which increases low energy to a higher level in an identical wave form, or as nearly identical as possible. This energy is increased until the loudness or amplitude of the sound or speech heard is the same as that transmitted. Now let us examine a typical amplifier and, in general terms, see how this amplification is accomplished. If you speak into a microphone, the mechanical energy of sound waves is converted into electrical energy by the vibration of the diaphragm of the microphone under pressure of the sound waves. This vibration in a carbon microphone causes the diaphragm to first compress and then release the carbon granules in accordance with the pressure of the sound waves. This varies the resistance of the microphone element, which in turn causes more or less current to flow in the external circuit. The changing current in passing through the primary of a transformer sets up a changing magnetic field, which induces a voltage into the secondary. This electrical energy must be amplified before it can be reconverted into sound. We can then apply this energy to the grid of a vacuum tube and thus cause the current through the tube to vary in accordance with the voltage applied to the grid. The changing current flow through the tube can now be used to develop a much higher voltage across a plate load and either drive a speaker or another amplifier tube. Each of these steps causes a loss of a portion of the energy. We restore the lost energy by use of batteries and a vacuum tube amplifier. Now, in more specific terms, let's study the construction and operation of a typical voltage amplifier. The heart of this amplifier is the vacuum tube. Power for the output circuit is supplied by a B supply, in this case a battery. The positive side of the B battery is connected through a resistor to the plate of the tube. The negative side of the B battery is connected to the cathode. Bias voltage is supplied by a C battery, with the positive side connected to the cathode, and the negative side connected through a resistor to the grid. The output is taken across the plate resistor and the power supply. The input is applied across the grid resistor. When a small signal is applied to the grid, it varies the difference in potential between the grid and cathode. This causes the current flowing through the tube to vary in accordance with the difference in potential between the grid and cathode. This varying current flow through the tube causes the voltage across the plate load to decrease and increase. This voltage change across the output is an amplified reproduction of the input. It should be noted that the output voltage and the input voltage are 180 degrees out of phase with each other. Now, suppose we place some values here. The B battery has a potential of 200 volts, and the load resistor is 10,000 ohms. To compute E2, or the difference in potential between the plate and cathode, we must subtract E1 or the drop across the load resistor, from E3, or 200 volts. Therefore, we must first compute E1. Let's say that the bias is minus 9 volts, resulting in a static plate current of 6 milliamperes. The input signal has an amplitude of 1 volt. Using Ohm's law, we find that if we have 6 milliamperes of current flowing through a 10,000 ohm resistor, there is a 60 volt drop across the load. Subtract this 60 volts from the supply voltage of 200 volts, and we find that the difference in potential between the plate and cathode is 140 volts. When the positive portion of the signal reaches a peak of 1 volt, there is a difference of potential between grid and cathode of minus 8 volts. This is found by subtracting plus 1 volt from minus 9 volts. This reduction of the voltage difference between the grid and cathode allows more current to flow. If the current flow increases to 8 milliamperes, this causes the voltage across the load resistor to increase to 80 volts. The voltage between the plate and cathode will consequently decrease to 120 volts. When the signal voltage goes to a negative peak of minus 1 volt, the difference in potential between the grid and cathode becomes minus 10 volts, computed by adding minus 1 and minus 9. This increase in potential causes the current through the tube to decrease to 4 milliamperes. The voltage across the load resistor now decreases to 40 volts. And the plate to cathode voltage increases to 160 volts. Comparing the voltage change between the grid and the cathode to the voltage change between the plate and cathode, we find that there is a 2-volt change in the grid circuit. And a 40-volt change in the plate circuit. We have thus amplified the signal voltage 20 times. This amplified voltage is applied either to another stage of amplification, a loudspeaker, or some other device which uses the amplified output. It should be especially noted that the original signal influences only the current flow through the tube. And the plate voltage change becomes a new signal, which is an amplified reproduction of the input signal. The amount of bias placed on the tube determines its operating point. Practically every type of tube manufactured requires different plate voltages as well as bias voltages for particular modes of operation. A good tube manual will give the proper voltages for the condition under which the tube operates best. The saturation and cutoff voltages can be determined without a manual. A meter in the plate circuit will show how much current will flow when a fixed B+ voltage is applied. If we increase the plate voltage until a further increase makes no further change in plate current, the tube is then saturated. Applying a specific negative voltage on the grid decreases the plate current. This negative voltage is increased until the plate current meter reads 0. The tube is now cut off. The relationship between plate current, or IP, measured in milliamperes, and grid voltage, or EG, can be plotted on a graph. As a line is drawn from point to point, we derive a characteristic plate current curve. Note that we do not get a straight line, but a gradual movement upward until a point of saturation is reached. That portion of the curve which is straight is called the linear portion. If we apply the amount of bias which allows current to flow only within the linear portion, we are operating the tube as a linear amplifier, or as it is called, a Class A amplifier. In this type, the grid is most sensitive to a minute change in grid voltage. When operating a tube as a Class A amplifier, make sure that the signal voltage, shown here as the lower waveform, does not drive the tube beyond the limits of the linear portion of the curve. This will avoid distortion. If we bias the tube at or near cutoff, it is a Class B amplifier. Note that plate current represented by the upper waveform flows for only slightly more than 180 degrees of the input cycle. If we bias the tube between Class A and Class B, we have a Class AB amplifier. Again, note the relationship between plate current flow and the input cycle. If we bias the tube below cutoff, we have a Class C amplifier. This class of amplifier is almost exclusively limited to radio frequency applications. In a Class A amplifier, the plate current flows during the entire input cycle. This makes the Class A amplifier the least efficient, yet the most sensitive. As another example, in a Class C amplifier, plate current flows only during a portion of the positive half of the input signal and is cut off at all other times. The Class C amplifier is the least sensitive, but the most efficient. Amplifiers are also classified according to type of service, whether they are to be used as a voltage amplifier or a power amplifier. Most circuits contain several voltage amplifiers and one power amplifier. However, there are exceptions, especially in radio transmitters. A voltage amplifier is designed primarily to deliver a large varying output voltage to its load circuit. In order to accomplish this, there must be a relatively high value of load impedance. For a given vacuum tube voltage amplifier, the impedance of the load is usually as high or higher than the plate resistance of the tube. A tube manual will give the plate resistance for the tube selected and its recommended operating voltages. For voltage amplification, the most common choice of tubes is the pentode. There are 4 general methods for coupling the output of an amplifier stage to a following stage or to a load. They are resistance capacitance, impedance, transformer, and direct coupling. Each method has its own particular advantages and disadvantages, and therefore is employed in circuits where its advantages can best be put to use.